Hello everyone, welcome to Electric Motors course. In this lecture, we will discuss about torque equation of DC motor. So before understanding and going to the torque equation of DC motor, let us understand what is torque in general, and when it is applied to the DC motor, let us understand what is torque in DC motor and what are the different types of torques in the DC motor. So first of all, we already know that the torque, the meaning of torque is, it is the turning or twisting force about an axis, right? So if you consider, let us consider a wheel, there is a wheel of radius r, Now on this circumference, a circumferential force is acting on, it is shown in this direction, circumferential force, that is on the wheel, a circumferential force is acting, and the force acting is given by F newtons, and the wheel is rotating in this direction. Let us consider it is rotating in this direction with an angular speed of, let us say, it is rotating by an angular speed omega, which is given by, we know this formula already, 2 pi n by 60, 2 pi n by 60, and we can assume that the wheel is rotating at a speed of n rpm. The wheel is rotating at n rpm, n rotations per minute, and if you consider the angular speed of the wheel, this will be this, omega is equal to 2 pi n by 60. So a torque means it is the turning or twisting force about an axis, So let us understand the relationship between the torque power and this angular velocity, So work done in one revolution, if a wheel is rotating one revolution, whatever the work done in one revolution, let us take it as W, work done in one revolution. So we know that the work done is equal to force into distance traveled, right? So the force applied, circumferential force applied on the wheel is F into distance traveled in one revolution. So since it is a wheel, the distance, if it is started from this point, it will cover this rotation and it will again come back to this. This will be one complete revolution. So distance traveled in one complete revolution is circumference. So we know that the circumference of the circle, it is 2 pi r. So this is the work done in one revolution, of this wheel. So if you consider the power developed in this, we know that the power is equal to work done per time. So for this wheel, if you consider the work done is this F into, it is F into 2 pi r, divided by the time taken for one revolution. This T is nothing but time taken for one revolution, and we already assume that it is rotating at n rotations per minute. For 1 minute it is taking n rotations. So if you consider for one revolution, the time for one revolution, we know that the speed and time are inversely proportional. So since the speed is n rotations per minute, if you consider this for seconds, it will be n by 60. So time taken will be, it is inverse, that is 60 by n. So time taken for one revolution is 60 by n. So if you rewrite this, we can write this as F into the radius r, and we have the 2 pi into n divided by 60. So if you rewrite this F into r, we know it is the torque, that is force acting about an axis. That is F into r, r is the radius, that is torque, into, we have the 2 pi n by 60 we have considered, it is the angular speed of the wheel, so it is omega. So this is the relation between the power developed, torque and the angular speed. So this is in case of general torque power relation. So same concept is applied to the DC motor, wherein the DC motor which takes the electrical energy as the input and gives the mechanical energy as the output. The mechanical energy is tapped at the rotor part connected to the shaft. So shaft is rotating, that is mechanical energy. Now since there is a rotation, there exists a torque, because torque means it is the twisting or turning force about an axis, right? Since the rotor is rotating, shaft is rotating, there will be a torque. So torque, we need to consider this torque for the DC motor. Let us say the total gross torque developed by the armature of the motor. Armature of the motor means the torque developed in the rotor part that is armature. Let us take TA is the total or gross torque developed in the armature of the motor. It is also called as armature torque since it is developed in the armature. So we call it as armature torque. And this armature torque is developed in the rotor part of the armature, that is in the rotating part. The mechanical power developed in the armature, we know that the mechanical power developed in the armature is PM. Let us consider the mechanical power, gross mechanical power developed in the armature. This is given in terms of electrical quantities, is the voltage at the armature into the current at the armature, current through the armature. That is, voltage developed in the armature is the back EMF EB, and current flowing through the armature windings is IA. So this is the mechanical power developed in the armature. So as seen from this power equation, so if this speed of the motor is in n rotations per minute, then we can write the equation for torque, power in armature, this mechanical power in armature can be equated to the torque developed in the armature into the omega, that is angular velocity. That is, by using the equation we have derived here, the relation between power, torque and angular velocity. In case of the motor, this is for general wheel. We are considering the same equation for motor. For motor, we have the mechanical power developed. This mechanical power developed is equal to the torque developed in the armature into omega. This again, omega remains same, that is 2 pi n by 60, because we have also considered the motor is running at n rotations per minute. So since PM is equal to TA into omega, we can write the equations for substitute PM is equal to EB into IA here. So if we substitute PM is equal to EB into IA, this is equal to TA into omega. So back EMF, we already know the equation for back EMF in terms of the speed, the number of poles, flux per pole, and the number of conductors. It is phi ZNP by 60A, where phi is the flux per pole, Z is the total number of conductors, N is the speed of the rotor, P is the number of poles, and A is the number of parallel paths. For wave winding, number of parallel paths will be equal to 2, and for lap winding, number of parallel paths will be equal to P. So if you substitute this EB here, the equation of EB here, we will get the phi ZNP by 60A into IA is equal to TA, and we also know omega is equal to 2 pi n by 60. So upon solving this equation, we will get the torque equation as. So you can see here the n gets cancelled, 60 gets cancelled. So if you write torque developed in the armature. Torque developed in the armature, which is equal to TA is equal to this 2 phi will be taken to other side, so this will become 1 by 2 phi into we have left out quantities are phi is there, IA is there, this IA, and as well PZ is also there divided by A. So this is the torque developed in the equation of the torque developed in the armature of the DC motor. Or if you calculate 1 by 2 phi value, we can write the torque equation as the torque developed in the armature 1 by 2 phi value will be 0.159 phi into IA PZ divided by A. So this is the torque developed in the DC motor. So if you look at the equation, the torque developed in the armature depends on the flux per pole, depends on the armature current, depends on the number of poles and number of conductors and number of parallel paths. So once you design a machine, DC machine, for a DC machine, the number of poles will be constant, the number of conductors will be constant, and as well as the type of the winding remains constant. So we can say that the torque developed in the armature is mainly dependent on flux and the armature current. Torque developed in the armature depends on since flux is variable quantity, field current changes, and depending on the type of the motor. In case of the shunt motor, the flux remains constant. In case of the series motor, the flux changes with respect to the load, since both armature and field windings are connected in series. So the torque equation mainly depends on flux and as well as the armature current. So this is the torque equation of a DC motor, the torque developed in the DC motor. So now let us understand there are different types of torques in the DC motor. Let us come to this point. Types of torques in the DC motor. So to understand this, let us write a diagram to understand what are the different torques available in the DC motor. So this is the armature part, we already know, since we have a armature here. Armature, the torque developed in the armature, the torque developed in the rotating part, that is armature, inside the motor is the TA. The torque developed in the armature is TA. So this developed torque should be transferred to the load, that is to the mechanical load, should be transferred to the load through the shaft. So if you transfer this generated torque is also called as the armature torque. Whatever the torque develops in the armature is the generated torque or armature torque. So TA is the armature torque. So here we have armature torque, and the generated torque will transfer to the load through the shaft. So while transferring, due to the friction and windage loss, due to the friction and wind resistance, there will be losses in this shaft, and the losses in this shaft are known as lost torque. The torque which is lost due to the friction and wind resistance is known as the lost torque, and the torque which is available at the load for doing the useful work. The torque which is available at the load for doing the useful work is called as the load torque, or it is also called as shaft torque, or it is useful torque, and which is represented by TSH, that is shaft torque or load torque or useful torque. So now from this we can say that the torque developed in the armature TA is equal to Torque lost torque we will represent it with Tf since it involves the friction and windage losses. So it is Tf plus this developed torque will be equal to lost torque plus the torque which is available at the load for doing the useful work, that is TSH. So these are the three types of torques that are available in the DC motor, that is armature torque is equal to the lost torque plus the shaft torque. Now let us assume the speed of the motor remains same for all along the shaft. For the speed of the motor from this armature to the load remains same all along the shaft, and it is rotating at n RPM only. It is rotating at n RPM only. Then the product of the shaft torque and the angular speed, that is TSH and omega. The product of the shaft torque, that is the torque at the load, and the angular speed is called as the net power output of the DC motor. Net power output of the DC motor, and this net power output of the DC motor is nothing but it is the output rating of the DC motor. It is the output rating. So if at all any motors are rated in any power, the power represents the net output power of the DC motor. Generally this net output power is expressed in horsepower. It is expressed in horsepower HP. So motor HP rating, you might have heard the HP rating of the motor, it may be 1 HP, half HP, 2, 3 like that. So HP rating gives the output power of the DC motor. So output power can be calculated by this equation. Output power is equal to the shaft torque into the angular speed. So mechanical power developed, we had one more equation, same power relation. This is the power developed in the armature. So from the armature the power is transferred to the load via the shaft, right? So in between at the shaft there will be some power loss. So those power losses are called as the rotational losses. So after the rotational losses we will have the output power. So this output power is equal to TSH into omega. So this is about the torque equation of the DC motor and as well as the types of torques in the DC motor. So important things in this concept is we need to understand how we got this torque developed in the armature. So this equation follows like this: 0.159 into 5 into IA PZ by A, this equation, and the types of torques, this TA is equal to TF plus TSH, and at last the net power output of the DC motor is equal to TSH into omega. Or we have one more power equation, the mechanical power developed at the armature in terms of torque, it is TA into omega. So these are the important equations we must understand from this torque equation. Thank you.